Hello and welcome to Module 9. This is going to be about nuclear energy. We're going to start out by talking about radiation exposure. And so without further ado, personal annual radiation exposure. And the first thing I'd like you to do is take a look at the first video in the Q list of videos about whether radiation is dangerous or not. So that's how I'd like you to start. And once you've watched that video, come back here and we're going to start by doing the personal annual radiation exposure. And the way I'd like to talk about this is by doing it worksheet style and just explain to you the different ways that you are exposed to radiation so that you can understand your daily exposures. That way we can start to talk about abnormal level exposures and then how we produce energy with exposures. And with this part of the lecture comes an assignment sheet that you are also asked to fill out. It's worth 20 points to your course credits, and it's an additional assignment sheet that you can do hand in hand while I'm explaining your exposure limits, or you can just do it directly after watching this video part 1. So you don't have to worry about setting up calculation table. And so first off, we're going to just talk about exposure data and just the amount of millirems, and these are rodons of exposure mans. So this is millirhodons exposure mans within these limits. And that's what this number is basically talking about, what is safe and healthy versus unhealthy levels of exposure. So how much to get sick is 25,000 millirems. And how much to die is 35,000 in 60 days. Or if you're going to die within 2 weeks, you have to have 50,000. And then for a small or instant death, you need over 100,000. And that's a huge exposure limit, like so much that you wouldn't even get this exposure limit if you were exposed to a reactor core within a reactor facility producing electricity. This is weapons grade exposure cores. So starting off on our sheet and creating a total for your amount of exposure, dependent on what altitude you live at, you are more exposed to cosmic radiation. These are your cosmic or extraterrestrial, so your atmospheric or sun-based radiation exposures. And so if you live near sea level, you're about 26 millirems, where if you live at higher elevations over 50,000 feet, you are at 47 millirems. So please take a moment and mark down how many millirems so that you can create a millirem total. And if you need to, look up your elevation in the place that you live or the place that you spend most of your time. The next radiation exposure is based on terrestrial, and so this is your soil and ocean exposures. And if you live within 200 miles of the Gulf of Mexico, give yourself 16, the Atlantic Ocean 18. If you live in the Colorado plateaus because of all the uranium-rich soils, give yourself 63. And if you live anywhere in the continental United States that's not near one of the oceans that we're talking about, give yourself 30. Most of us, if we're in Valhalla area, will be near the Atlantic Ocean, and so therefore we'll give ourselves 18. Building materials. If you live, specifically sleeping, if you are sleeping in a residency made out of stone, brick, or concrete, please give yourself the appropriate marking of millirems. And if you happen to sleep in the basement, and this is even if you're sleeping in the basement of a home built with wood construction or vinyl construction or some other building material, if you happen to have your sleeping room is in the basement part of your home because of your radium exposure and things like radon and soil, you will give yourself a 9 millirem exposure. So please add that. So for example, if you had a concrete home and you slept in the basement of that concrete home, you're going to give yourself an 18. Where if you are living in a wood home and you just happen to have your bedroom be in the basement, give yourself a 9. So give yourself the number that is appropriate to your home in that section. Next one is power plant exposure. If you live near a nuclear power plant. And so for most students in this class, since you are at Westchester Community College, and that is located near Valhalla or in Valhalla, you are probably in Westchester. And so if you are in the outer part of the circle on this radius, this little outer part circle, give yourself a 0.0001 millirem. And if you happen to be in the 10-mile radius, the little inner circle, give yourself a 0.0003 millirem for your nuclear power plant exposure. Now, the next part requires you to do a little research. So I'd like you to hop on to your .gov or your state, and I give you the little SKU for New York, but if you happen to be in another state, please use the appropriate state, and add up how many coal-fired natural gas fossil fuel-based power plants will be near you, because you will have your standard radiation exposures from radium and thorium found within coals and fossil fuels and other waste materials in those fired power plants. Give yourself a 0.3 for each one. So for example, I live in Ridgefield. I am near 3 facilities, so I will give myself a 0.9 on my number scale for when I'm adding this up. But give yourself the appropriate number for the number of power plants near you on this part of the question. Next one is about food. So we eat radioactive things. We are radioactive things. We are carbon-14, right? We are a living thing. We are carbon-14, which means we create radiation ourselves. And so if you happen to eat animal-based food, you have radiation exposure from doing that, and you can give yourself 120 millirems. If you happen to only eat that meat-based food, so that animal-based food, 3 times a week, give yourself 60. And animal-based food counts as things like cheeses. So, vegans can skip this question. But if you ain't the vegan, you go to the other questions. If you happen to eat quite a bit of bananas, carrots, or potatoes, and you eat them about 3 times a week, you are consuming potassium 40, which is also, potassium 40, which is also radioactive. And so therefore, you give yourself a 20 millirem. And if you happen to have a very normal vegetable intake, you are eating a vegetable a day, give yourself 30. So for example, if I'm eating meat every day, I give myself 120. And if I happen to add one of these 3 veggies often, I'm going to add 20 to that, giving myself 140. And then I do eat my vegetables every day. And so I'm going to give myself another 30 onto my 140. And so you're going to add together the numbers that are appropriate for yourself. Water. We drink water. We bathe in water. We are exposed to uranium and thorium in water. So give yourself 10 millirems. Next one is breathing. We breathe air. Air contains radon. Give yourself 200 millirems for radon. Jet planes. This is once again one that's going to be variable based on students. When you are up in the plane, you are farther up in the atmosphere, therefore exposed to more cosmic radiation. So even in that duration of time, you're going to give yourself a 0.5 on your millirem for each hour of flight. So if you're on a 2-hour flight, you're going to give yourself 1 millirem. If you are on an 8-hour flight, you're going to give yourself a set of 2 millirems, right? You're going to just add up your millirems on your flight times. If you are walking through a scanning system, so if you pass through a scanning system, please give yourself a 0.002 for each scanning system you've walked through. And do this for the number of flights that you've taken this year and the number of X-ray scans that you've had this year. Add up your total and put that in your box for your total. Some other sources, if you sleep next to some living thing. Now, this means not your goldfish. You can skip your goldfish. But, if you're sleeping with your puppy or your kitty or another human being, please add the number of millirems to those human beings or those animals that you're living with. You are all carbon-14, and just think the love. You're radiating each other in your sleep. So much snuggles, right? Nuclear fallout, all the weapons testing we've done, you're going to give yourself a 0.1. Porcelain crowns and false teeth, if you have any fillings, give yourself a 0.07 for each filling. Luminous objects that are LCDs, LCD luminous items, if you happen to sit yourself in front of them, each LCD luminous item that you kind of put yourself in front of daily, give yourself a 0.006 for each one of those. You're going to add 1 millirem for each hour per day you spend watching TV or sitting in front of a computer. And then finally, you're going to give yourself a 0.008 millirems for each smoke detector in your home. So add all those up, and I'm going to pick up with medical sources and totaling up your numbers. All right, picking up right where we left off on totaling. We left off right on doing smoke detectors. So finish up your smoke detectors. Once again, the LCDs and the computer and TV exposures that we're giving us with MIREMs, give yourself the hours for the TV and the computer. Smoking. If you are a smoker, you are radiating your body. It's not the only health disaster that comes with smoking, but it's one of the other things that you can pick up on. And so give yourself the appropriate smoking number. The smell of cigarette smoke means that you are smelling embedded, which means that there is radiation exposure still within that region. So if you are even smelling cigarette smoke, it means that you are having radiation exposure. So if you happen to live with somebody who's a smoker and you happen to have to smell that, you're having minor radiation exposure. So please give yourself the appropriate number, even if you're just around smokers. Which brings us to medical exposure. Now, the medical exposure is a long list, and this is based on your personal exposure. And this is actually why doctors will ask you things like if you've had any other testing with any other doctors, is because they want to make sure that you haven't been overexposed with different amounts of radiation. While the radiation that your body can handle is one, natural, because we evolved on this planet, so we evolved under a natural amount of radiation. There is unnatural amounts that can affect the body and tip the balance in a negative way. When you think of something like a chemotherapy, it is a radiation exposure therapy that will eventually tip the body to a point where the body might be able to handle that radiation exposure, but things within the body cannot, zapping them out. And they're trying to walk that line of that very thin balance in there. And so it's something to keep in mind what type of radiation exposures you're playing with. But X-ray exposures. So once again, the way it works is I'm bombarding you with electromagnetic radiation. It happens to be small particle waves that can move straight through your squishy parts that bounces off your hard parts, hence why it picks up on things like bone, right? That's where it's coming from, or really dense organs, things like that, depending on the level of wavelength, so the size, proportions of the wavelength, what I'm picking up on and what's bouncing back. So please give yourself a totaling, and there's 2 pages. Here's one for CT scans, and then right below radiation and chemo treatments. And that's why they'll say you've had one treatment, not one session of chemo, but one total treatment over a course of time. When you have a course of time, if you go for one treatment of chemo, which might be done over like 6 weeks, several months, whatever it happens to be, and then they decide to put you through another treatment of chemo, they're talking about 400 millirems and then 400 millirems again. And so that's what they're talking about when they're doing that. But please give yourself an appropriate number and fill it in the box for your various health concerns. Please do this for the course of 1 year. I'm not concerned past the year because your body will have flushed out that material. You have the ability to regenerate. So as the final little bit, please give yourself what your total millirems are. And then there's a small essay question in the assignment basically asking, what is your total number? Do you feel that your exposure limits are high, or what safety limits do you think might be in place? So on and so forth. But the thing to keep in mind is that the standard allowable is 5,000 millirems per year, and that is an allowable, healthy, normal amount. With that said, the average U.S. citizen, now in other parts of the world, they have much higher. So like if you lived in Beijing, China, you are getting way more millirems just from your exposure to pollutants in the atmosphere, right? So your breathing is bringing up a lot more material. But the average person in the U.S. is exposed to 620 millirems. So how do you stack up compared to that average, Talking a little bit about dosage, here is the national average of radiation. This is your regulatory numbers as you're working through. And then we're going to begin talking about nuclear power, but I'm going to actually end this and pick it up with a part 3. So while this looks like a really long set of videos, they're not. I just want to cut everything really cleanly so that everything makes sense. Hello, welcome to Module 9. This is about nuclear power. We're talking in Chapter 14, and this is actually video part 4. I know that there will be a lot of videos for this specific subject matter, and I apologize for so many videos. This is just a topic that needs to be covered well, and the book gets to be a little outdated as far as text, so you can't lean as heavily on text, and I really want to make sure that I give you guys a very complete knowledge. So, talking more about fission, we left off just talking about uranium and how we're going to utilize uranium to produce electricity, and that we like to use uranium because it's easy to manipulate. I can manipulate uranium, specifically the weight of uranium-235, very easily by bombarding it with one neutron, which fluctuates its weight into the 236 range. So it keeps its 9 protons, but it gets up to a 236, which makes it unstable. It can't exist naturally at 236 or 237, and therefore it will break apart, making krypton and barium and throwing away some extra neutrons in doing that. With that said, uranium naturally comes in uranium-238. That is the most common form of the uranium set, and that something as light as uranium-234, which is considered lightweight uranium, and uranium-235, which is considered middleweight uranium, does exist, but it exists in very small percentages. Less than 1% of your average uranium rock will contain that very rich, easy to manipulate, good to produce electricity form of uranium. As far as keywords, one of the keywords you need to know is chain reaction. A chain reaction is when I take that neutron and I bombard it with a atom that is unstable, like uranium-235, and when it splits, it throws off extra neutrons that it doesn't need. And those neutrons then hit into more uranium-235 or any radioactive material, and it causes them to split. If I can split and go from one generation to another generation of splitting, and I can do this at least 2 times, I have what's called a chain reaction. Which brings me to critical mass. Critical mass is when I reach a point where they are splitting, so the atoms are splitting, making 2 new elements, so they're splitting apart, but I can no longer rein in the neutrons and the atom splitting, so that it will reach a point of critical mass and continue its chain reaction until it runs out of material. And so there's no going backwards from critical mass. Hence the statement critical mass. That's where that terminology comes from. I cannot stop the chain reaction when I've hit critical mass. So going into uranium itself, it's known as uranium-235. That is specifically the one that we want. If you look at the periodic table of elements, obviously its atomic number is 92 because that's how many protons it has, but its atomic weight is normally written as 238, and that's because that's how it's most likely to occur naturally in the environment. I have the melting point, boiling points, but we won't be using either one of those. You're going to find it as a solid. It's a metal, but it's a yellowish colored metal. And it has a half-life of around 4.4 billion years. And it decays into thorium, which also has a alpha decay ability. So it becomes another radioactive material when it tends to break down. Uranium-235, which is the one that I'm looking for and I want to find within the uranium rock itself, because that's the one I can manipulate. That's the one that I can make unstable and decay on command, basically create its radiation on demand. That occurs at only about 0.7%. So like I said, less than 1% of the time. There is an advantage to using uranium, and that is the amount of energy that I get out of uranium is extensive. 35 tons of uranium, and I use 35 tons because that's the average uranium reactor core is loaded with about 35 tons of uranium. Hence, when I'm using that, can produce 90,000 megawatts per year. And when I fill my reactor core with that amount of uranium, I do not refurbish or replenish the amount of uranium in my reactor core until I use it all up. And that takes about a year to use, but sometimes longer. And so my average core is about 35 tons worth of uranium, and it takes about a year, sometimes a year and a half, depending on location. Compare that to coal. it would require me it would require 3,000 tons of coal to produce that same amount of energy, or 14,000 tons of crude oil. And just to get a handle on how much this is, one of these train cars is 55 tons of coal. And this little tankard right here is 28 tons of crude oil. So this is 1 kilogram's worth of a uranium pellet, and that is equivalent to this, which is equivalent to this. And so it's quite astounding how much energy is packed in nuclear reactions. You think of suns like our star, like stars. Our sun is a nuclear reaction. We are doing fission and fusion all the time. So it's a huge amount of energy. The fuel cycle goes from mining to conversion. So I have to find uranium-235 out of what I have mined. Enrichment, fuel fabrication, power plants, reprocessing, and storaging and disposal. So mining is step 1. In the United States, we now prefer to do open cast pits, which is pretty much strip mining again. It's a little bit different because of the nature of uranium. We want to be safe about it, but we do open cast pits for uranium mining, which is very much like strip mining. And we don't do underground mining anymore in the United States. It's just not safe. But if we're getting our uranium from other countries, which we do, we totally get it from countries that still do underground mining. As far as where are our uranium stores in the United States, most of them are located in Wyoming, Texas, Colorado, New Mexico, and Utah. And we're pulling it right out of the ore within the rock. And when we pull it up, we pull out the rock, we then enrich the rock or break it down. And what we're left with is a powder. And the powder of the rock, or the rock powder that's left over, happens to be uranium oxide, or UO2. Interestingly enough, it looks exactly like Betty Crocker's yellow cake mix. And so in the industry, we just call it yellow cake as it's there. So here's an open cast pit. And here is a facility that was once a cast pit, which is now an abandoned uranium mine. And just a little artist graphic. Here is some old-timey pictures of underground. And like I said, we don't do underground much anymore. Here is how, if we are doing underground, or even if we're done with a facility, so it's a cast pit, but we're done with it and we're no longer going to use it, we have to set up these mitigation areas where we can check to make sure that we're not polluting groundwater and such with radioactive material. And here's the uranium oxide after it's been pulverized. So after we've pulverized the rock down, it's left looking like yellow powder. As far as uranium mining, like I said, we're not a big number. We're about 4% of the world's uranium stores, but you can see who has the most and where we're getting it from. Which brings us to getting that powder and turning it into something more. So enrichment. When we pull up uranium oxide, only about 0.7% of it is the 235 we need. In order to create the little pellets that we use and load into reactor cores, we actually have to turn that 0.7% into a 2 to 3% raise. So we have to filter out some of the uranium-238, not all of it. Like I said, I only need 2 or 3%, and that's a good number because it keeps the uranium at a level where it is radioactive and able to produce huge amounts of energy. When it's breaking apart, it's producing huge amounts of heat. But at the same time, it is not going to produce enough energy or enough heat to create a bomb. Our reactor plants cannot go or explode. So on that note, I'm going to pick up talking about the 3 forms of enrichment in the next video in a part 5. All right, Module 9, Nuclear Energy, Part 5. So enrichment, we have 7 forms. We talked about how we're trying to enrich it from 0.7% up to 2 to 3%. And we have the different weights. And so like I said, heavy weight is uranium-238, middle is 235, and lightweight is 235.4. 38 is considered stable. That's the one that breaks down every 4.4 billion years. 235 is the one that if I hit it with a neutron, it'll become the weight of 36 just for a moment, momentarily, a blink of an eye, and then it will bust apart because it cannot stay stable at that weight limit. And so it'll break apart and become barium and thorium. There are 3 types of enrichment method. The first one is gas diffusion, the next one is gas centrifuge, and the final one is laser separation. In the United States, the only one that we allow commercial sector to produce uranium for enrichment cores or pellet production is in the form of gas diffusion. That does not mean it's good technology. It's actually old and outdated, and a centrifuge system would be better. But we have a political issue in the United States where no politician wants to vote to change laws to allow for other forms of nuclear power uranium production within our country, because that would give them the black mark of voting for or against nuclear power, which makes them not want to have any actions. And so it's something that's being highly regulated but can't change its regulations. So we're using an outdated technology. But I'm going to explain them all. And I'm also going to say that we do laser separation, but only for military purposes in the United States, but it does occur. So on that note, gas diffusion. So I take the uranium oxide, so the UO2, and I change it to uranium hexafluoride, and that's not that hard. I just have to mix it with fluoride when I'm heating it up. So I heat up my uranium, it drops the oxygens, and it picks up the fluoride because it prefers that in its gas form. Then once I have it as uranium hexafluoride, I can push it through a cylinder system, which has porous membranes on either side. And the small uraniums, the ones that are 234 and 235, can fit through the porous membrane holes, where the uranium 238s are a little too big, and so most of it can't fit through the porous membrane holes. And therefore, I end up with this area where I have mostly 234 and 235 uranium, just enough, 2 or 3%. The rest is all uranium 238 that did squeeze its way through. And it makes the perfect number necessary, which then I can cool down and compress. And once I cool it back down, I can take it from its solid form and press it into these little pellets. And that's basically gas diffusion. The next one, gas centrifuge, is incredibly efficient. Once again, I take my uranium 235 and I make it into a gas in uranium hexafluoride. And so once I have my uranium hexafluoride, or my fluoride 6, I can then take that gas and put it into a cylinder system and spin it. The heavy stuff, the uranium 238, sticks to the outside, and the lightweight stuff stays to the inside. So it basically sets itself up based on weights or densities as it works its way out. And then I can just stick my syringe in the center and syringe out my 235 and my 234 material from the center. And then I can just cool it back down to room temperature, which puts it back in solid, and I can press it into a pellet. Last one is laser separation. This one is done with a laser system which has an optical module and a separation module. There is no reason in a commercial sector why we would need to use laser separation unless we needed to enrich uranium at such a high level. And so this is really only needed for weapon application only. But what it is it's a laser optical system where I put my uranium hexafluoride, once again, I have it as a gas in isotopic material, into this kind of like black box system that has a laser, and it hits the fluoride particles with the laser and it bounces back, and the splay on the way that it bounces back will identify the size of the particle. And then the optical module has a digital separation system on it that basically has like a little computer inside it with a little suction, and it just suction hoses the gas modules that I need. And it sounds complicated, but it's not. It's actually a pretty simple robot, to the point where some colleges have a robot that does like an optical laser system that just doesn't do the module separation part of the system, right? So it's not as complicated as a tool as it sounds, but that's the optical laser separation system. Like I said, there's no use for it in commercial application, but we do it in the United States. We do it for military application. So, optical system. That brings us to talking about our reactor core. So now I have my uranium-235 and I press it into a little pellet, and those pellets can get loaded into an assemblage of a reactor core system. And so I can take, and once again, just reviewing chain reactions, I can take and now make my fuel. So I take my uranium hexafluoride and I convert it back into uranium dioxide, so it goes back into its powder form. And then I press those that powder into pellets, and those pellets then get loaded into a zircon alloyed shaft. And the reason why it gets loaded into that sort of material is because a zircon alloyed or stainless steel shaft that is a hollow tube will allow neutrons to flow freely through them. So that means that the tube sitting next to another tube will allow a neutron to actually pass through the material from one tube to the next, so that I can create another chain reaction on the other side. So I can have actions going from pellet to pellet within the pellet itself, and from one pellet to the adjacent pellet through the tube material. Now, because of that, we need to be able to control this material, and that's where control rods come in. So here's first my little assemblage. So I have my little pellet, and that gets loaded into my fuel rod, and my fuel rod gets loaded into my assemblage. My assemblage is then spliced up, and between different assemblies, to kind of blockade them into groupings, I then put in control rods, and I'll have about 120 to 180 control rods within my assemblage. Those control rods will be made out of cadmium or boron, and the reason for that is because they capture neutrons. They like to absorb neutrons, and so if I capture the neutron, that neutron cannot go on to bombard any other uranium, making any type of chain reaction occur. And so I can stop or slow down the chain reactions by dropping my control rods in and out of my assemblage bundles, which brings me to going back to this picture that has this little setup here. This is a control rod. It's on one stem, and this stem can raise up and down within the assemblage to make the reaction occur faster, creating higher temperatures, which allows me to make more steam, which allows for more steam turbine turning. More turbine turning means that I'm turning my generator more. The more I'm turning my generator, the more electricity, right? Electrons jumping. So I can make greater amounts of electricity or lesser amounts of electricity based on the raising and lowering of my control rods. That brings me to reactor cores. Now, I had mentioned in previous slides that we have a lot of different types of ways that we produce electricity in the world. As far as nuclear reactor cores, there are smart nuclear reactors and there are mini nuclear reactors. Both of those systems are now in operation, specifically in Japan. That's the country that comes to mind right away that has these. In the United States, we allow two. We allow boiling water reactors and we allow pressure water reactors. So BWRs and PWRs. Both of them are what's called light water reactors. This can be confusing because they use a lot of water and the water that they use is called heavy water. Now, on this note, if you have not watched the videos showing a little bit about the different reactor cores, please take a pause and watch those videos. They explain more on light water reactor cores, both boiling and pressure, but I will pick up and do a quick overview of them, and then I will move on to the next sector. Hi, welcome to Module 9. We're going to be talking about nuclear energy. This is moving into Chapter 14 content. We're going to talk about fusion. And to start out, nuclear energy, as far as producing electricity, can be seen as the great hope for energy independence for many nations that are highly driven towards electrical need within their power supply, such as the United States, where everybody expects to have power. It's not like it's an up-and-coming grid source, and so it's something that can produce a lot of power in small space. As far as material that we use uranium as our general power source for production of electricity. but plutonium can be used. I'm going to point that out because we'll talk about MOX fuels and mixed reactor cores, even though they're not legally allowed in the United States. They do exist in countries like Japan. But plutonium is hard to utilize. It produces a lot of energy, not electricity, a lot of energy, and therefore plutonium is often seen as a weapon grade based radiation material, where uranium is seen as something that can be more utilized within a commercial utility space. As far as brief history, the Nautilus is considered the first nuclear-powered sub, and that was in 1953. As far as nuclear power plants and electric grid supply in the United States, the first one was in 1957 in Shippingport, Pennsylvania. 3 Mile Island is the first reactor core meltdown issue that happened within the United States. There has been other nuclear power plants that had had problems prior to, and that happened in 1979. And the worst nuclear disaster on record was Chernobyl in 1986. As far as United States nuclear power plants, and this is material that I should really preface and say, please lean heavily on what I'm providing you, because I'm giving you the current numbers and data, and the book is already outdated on nuclear power plant numbers and such. And if I ask you about how many there are in the United States or things like that, those sorts of questions at any point in time, please reference the most current numbers. We want to be up to date and current, and kind of wax over that part in the material in the book that's already out of date. But as far as the United States has the world's largest production of nuclear power plants, we have the most power plants in the world. There are exactly 104 nuclear reactor cores in the United States, exactly 100 of them operational, but there are 104. 4 of them are still existent, and they're still running in the sense that they have holding pools and other things, and you'll see that information as we continue through these slides. There are 5 that are under construction, but the construction of those nuclear power plants in the United States keeps getting halted, and then it's active again, and then it's, so we'll see if any more come online. As far as how many have come online, the last one to come online came online in 2011, and that one was predated or set to come online way back in 1979, and that has to do with after the 3 Mile Island nuclear core meltdown, which was considered a safe handling, but it's up to opinion. If you lived in that community, it was a scary time. After that, no new leases or facilities were really allowed, and we have very strict laws in the United States allowing and not allowing nuclear power. Basically, there's been a 30-year period where we have seen no real new builds. And while there are some set to come online in 2020, we don't know if they'll actually get completed, because there's a lot of litigation that halts and a lot of catches with these new facilities, and there's all sorts of problems. And so it's a highly political action. It's a difficult one. It can be dangerous if done wrong. With that said, I don't want you to live in fear of a nuclear power plant. I want you to live educated. I want you to know how they work and why they work, and what to be scared of and what not to be scared of, so that we can have a well-educated discussion about how we provide power for ourselves. I know that was a wordy slide. Please just take your time, read through as needed. Nuclear power plants in the United States, as I said, there are 104, but at the time that we were building all these, which was between the 1950s and the late 1970s, they were all sanctioned to be built where there was the highest population of people, which were on the East Coast. And so 1/3 of all nuclear power plants are actually right up in the New England area. So right up here, housed around New York and Connecticut and Vermont, Massachusetts, and down in Pennsylvania and New Jersey. You can pretty much see like the DC, Maryland line on up is where most of them are. There are mostly on the East Coast, and there are a couple on the West Coast, and there's almost none where there's very few people in population. And there's multiple reasons for that. Nuclear Regulatory Commission, the NRC. Now, the Nuclear Regulatory Commission is the group or organization within the federal government that regulates all nuclear power within this country. It is a government entity. It is highly powerful in the sense that it's given a lot of oversight, and nuclear power is one of the most highly regulated forms of energy that we get on our electric bill. So it's pretty safe. It's a pretty regulated facility. It's one of the least dangerous jobs that you could have, is working within the regulatory system. And so things to keep in mind. There are what's called smart nuclear reactor cores and mini nuclear reactor cores. Those are both not legally allowed in the United States. So in the US, we are allowed to build two types of reactor cores, and we have only two types of reactor cores. So all 104 reactor core systems, all 104 nuclear power plants in the United States are either pressure water reactors or boiling water reactors. There are benefits and downfalls to both, and we will talk more about that as we continue on. So, as far as worldwide, there are a lot of other nuclear power systems. There are around 430 commercial nuclear power reactors in the world. There are 31 countries that are legally allowed to produce nuclear power. They provide about 11% of the world's electricity grid system. You can basically see there's some countries that are completely done with nuclear power and are phasing it out. So as these reactor cores come of age, they're just going to get rid of them. Like Sweden and Germany, they have voted to phase them out. So as they come of age, places like Western Europe rely incredibly heavily on nuclear power. France gets most of its power from nuclear. It doesn't take up a lot of space and it doesn't require a lot of fuel. It's a really easy choice for a small country. As far as where everybody gets their power, this is the 2014 map of world nuclear power, and you can basically see who's got what and where. This is the breakdown within country to country. We have 104, so we got a really big wide bubble, but it only provides about 20% of our energy needs, as you can see, where France, I believe they have 56, it's on one of the slides. They have like 56 power plants, and it provides over 75% of their electrical energy needs. Here's that list. So, 58. I was off by 2. So 58. Japan also has a very high number. So 54, Japan. So it's pretty much United States, France, Japan, and then Russia have the most in listing order of top 4. That brings us into fission of the molecules. And so we're going to talk about breaking down uranium and the different splittings. And this gets me into talking about nuclear fuel cycle. So we're going to start working on the nuclear fuel cycle itself. And we're going to start out by mining and creating that uranium that we need. And so right off the bat, the material that we're going to want to use to produce the electricity is to allow a nuclear reaction where I'm going to take the nucleus of the atom and actually split it into 2 separate atoms. And the material that I'm going to do that with is uranium, because it's easy for me to manipulate uranium. I can do it very easily by bombarding it with neutrons. So on that note, I'm going to pick up with a part video that's going to talk about nuclear fuel cycle. Hi, Module 9, Nuclear Power, and we are on a video part 6. Let me get rid of this little record box. Boom. Okay. So hopefully you've taken a pause and you've watched the reactor core videos that show an actual reactor system and one about cleaning the core. And so we can pick up with the light water and boiling water reactor cores. So pressure water reactor cores, PWRs, are kept under pressure so that they are not allowed to boil. And this is a closed loop chamber. So this water never leaves this core. It stays within the core itself. That water is then put in thermal contact, so through the pipe tube with a set of water next to it. This is the water that's allowed to boil. This water is allowed to turn a steam turbine, and that steam turbine then turns a generator. The boiling water is also not allowed to leave the core. It's actually the water that comes in from outside that we pull in, that's the cooling water, that is allowed to come in and cool off the boiling system so that it recondenses and can go through the turbine again. And that's the water that's actually allowed to go up through the steam stacks. So in nuclear power facilities, those big wide stacks on top, those are steam stacks, and they only allow steam through, unlike in fossil fuel plants, which allow carbon dioxide and carbon monoxide. What's going up the stacks is everything that was in the water. So there is radiation in the steam stacks, but that's because there was uranium and thorium in the water that was being boiled as it was put in contact, thermal contact with boiling water. So none of this material is stuff from the core. Nothing is touching the uranium core material. Boiling water reactor cores. So this is the pressure water reactor core, right? And here's my condenser. This is the cool water that's going to cool the system. So closed loop, water never leaves. Closed loop, water never leaves. Condenser, this comes off a river. This is why things like Indian Point, the power plant that's closest to us, it actually slated to close. So this is going to be a very different class when I re-record it in next fall, right? So that's why it's located right on the Hudson. So on the other hand, boiling water reactor cores, or BWRs, are allowed to boil, so it's missing one of those loops. Now, pressure water reactors are considered safer, but they produce a little bit less power for their nuclear breakdown / transition because there's so many stages. As I transfer stages, once again, talking about conservation of energy, every time I'm changing stages to try to transfer this energy from this point to this point to this point to this point on the generator and then out to the grid. When I'm trying to do all this, I'm losing percentages. And so it becomes less and less efficient. So pressure water reactor, less efficient, but considered safer because it has two closed loop systems. Boiling water reactors are more efficient, but they are considered a little less safe because they go straight from boiling water to condensing to cool them off. Boiling water reactors are actually the older module of the two. They came first. These are the systems that were built in the 50s and 60s, and pressure water reactor systems were built in the 70s and are the ones currently being built today. We wouldn't allow a system to be built past this point in time. In this one, the reactor core is allowed to turn that water to steam. The steam is pushed through the turbine. Then it's recondensed, right? And then it's sent right back through the system. And so this is a boiling water reactor system. Power plants, basically after we are done with our fuel, so after we are done with the uranium oxide pellets, there is quite a bit of uranium-235 that can still be utilized. It's just being kept so far away from the other 235, since it's only enriched at 2 or 3%, that it cannot bombard the other particle with a neutron because they are so far apart within the pellet itself. And so one of the things I can do is recycle my uranium. I can take the pellets and I can chop them up and reprocess them, put them through a gas diffusion or gas centrifuge system and re-enrich them into pellets. This is something that's also not legally allowed in the United States, and it does have some political leaning as to why we don't allow it here. As I mentioned before, there is politics involved, and so therefore we don't allow it here, but it is allowed in many, many countries, like in France and Japan. And so they are allowed to reprocess and recycle their uranium into more uranium-235. And so that's one. And then the next step after it's been reprocessed, if you are allowed to reprocess, once again, in the United States, we just go directly to step 2. We go into long-term storage and then finally disposal, which brings me to the politics of the United States. We actually don't have final disposal in the US. We're still working on that problem as well. So reprocessing, once again, not allowed in the US, but might be, who knows? Like I said, might be re-recording, and a year or two from now, we might be allowing it. So I might be explaining something different. I take the fuel rods and I chop up the pellet, and I chop it up with an acid, which disintegrates out the zircon again and allows me to pick up on my uranium oxide, which I turn into uranium hexafluoride, and I put it back through the enrichment process. Some of the material that I will pick up this time will actually be plutonium. That will be under 0.5%. So 0.5% will actually be enriched plutonium, which can also do a radioactive action that can make power and electricity. And so we are allowed to do this. This is called a mixed oxide fuel, or MOX fuel. There are some reactor cores that are allowed to do MOX fuels. Japan is one of them. They're allowed to load each reactor core with about 20 to 35% of their fuel rods are allowed to be a MOX fuel rod. We do a lot of fuel fabrication, and the facilities that do this reprocessing fabrication exist in Belgium, France, Germany, UK, Russia, and Japan. Once again, just talking about the health factors and the risk and why we don't do it. We cite public health factors, but like I said, many other countries, and we've been doing this since '95, so it's not a new science. It's pretty much just like reprocessing the other materials, which brings me into storage and disposal. So once I pull out a fuel rod, if I'm not going to recycle it, the next stage I need to do is to cool it off. And this is a process called the spent fuel rod cooling. And this is where I put them in water. Now, water is a great barricade. It allows it to do a couple of more chain reactions as it needs to, but not enough to make power, so it can't boil the water, but it keeps the radiation within the water itself. And so I will put it into a storage pool, which will then hold individual reactor cores for a number of years, between 5 and 7 years. And then after 5 to 7 years, I will put it in what's called dry cask storage. Here is the storage facilities. As of right now, there is no nuclear disposal system in the United States. We don't put them anywhere. They actually stay right on site, but they are left in a sort of semi-mobile on-site form, so that one day, if we come up with a place to dispose of our nuclear spent fuel rods, we will be able to ship that energy there. So it's actually all on site, and you can see this lovely little setup here, which just gives you the metric tons of fuel rods that have been spent that are sitting in-house in various states. So like I said, pool reactor storage, we do it right in a pool. We put in our spent fuel rods, they get dropped down in their assemblages, and they're allowed to cool between 5 and 7 years. After 5 and 7 years, I can then pull them out of my pools. Here's another pool picture. And I can put them into a storage system. The storage system consists of creating a matrix. This is a butamin polymer bromosilicate mixture. And so the matrix starts out with a bromosilicate. Bromosilicate is better known as Pyrex, right? Pyrex glass, so highly able to hold heat. And then it is then cemented on the exterior, and it looks something like that for cementation. And this is my fuel rod assemblage. So now on this, I'm going to pick up with hopefully my last part video talking about fuel cycle, where I'm going to talk about storage disposal.